Today we're going to talk about stars, and in particular look at our sun first. But here's some basic information in chapter 10 about stars. We'll recall that all stars are comprised dominantly of hydrogen with some helium, most stars, and far lesser amounts of other elements. They exist as huge plasma spheres, plasma being the fourth form of matter after solid, liquid, and gas, plasma being a charged gas particles, fusing hydrogen into helium, producing enormous amounts of energy, as we saw in the last chapter. Although star masses can vary considerably, most have a mass between about 8/100ths of the mass of our sun and 100 solar masses. So approximately about 1/10 of a solar mass to 100 solar masses. So our sun is on the small size of the scale. One solar mass is the mass of our sun. Most visible stars are part of a multi-star system, unlike our sun, which is a single star, which is a good thing, because if we were part of a multiple star system, then it might be a more complicated scenario in order for us to have the right occurrence for life. Binary stars are stars that consist of two close stars, each orbiting about their shared center of mass. So there are a number of systems out there that are binary star systems. Our own solar system would be a binary star system if Jupiter had more mass. Jupiter is not quite enough mass to form another star. Also, other star systems with three or more closely spaced stars, but these are far less frequent. Most of the stars that you see in the sky when you look out at the night are binary star systems. And we'll talk about that more later in this chapter of why we see those stars and why they are not single star systems. Here's a bunch of stars in the large Magellanic cloud in the southern hemisphere. So this is something that we can't see here in the northern hemisphere. Looking at this to illustrate that there are over a quintillion number of stars in the universe. A quintillion is 10 to the 18. A million is 10 to the 6. So this would be a million millions of that, or a million billions. No, this would be a billion billions. So if you had a billion stars and you had all those into one group and took a billion of those groups of stars, then you would have a quintillion. Why do stars twinkle? This is not an effect of the star itself or the light coming from the star, but it's more of a local effect. It is the effect of the atmosphere affecting the light of that star, the atmosphere having variances in temperature, and these temperatures will refract the light a little bit differently, causing it to refract back and forth, giving it that twinkling appearance. Mostly an effect that you would see with a speck of light that was relatively small, hence you see the stars twinkle. You don't see planets twinkle as much because they are greater diameter pieces of light, and hence they don't. That variation due to the Earth's atmosphere is not so evident. How to understand stars? Well, the best way to understand stars is to study our own sun, because our sun is a star and it's close to us. So it would be best to try to understand the sun as best we could. Other stars can be more massive and possibly brighter than our sun. Other stars may be less massive and dimmer than our our sun. So hence there are variations, but it's always good to start with something that you know and start with a focal point. And here's the main thing is all stars are vastly more distant than our sun. Vastly more distant. So it's good to understand our sun and study it well as a example of a star, because it's harder to study the other stars. They're so far away. And we can make this comparison. We know that 99% of the human genome is the same as mice. If you look at mice and you look at a human being and you made a comparison, well, you would notice that they both had eyes, pairs of eyes, and they both have a nose and a mouth, and they both have hair and they have ears. And so if you study the characteristics of mice and compare that to humans, 99% of those characteristics are the same as humans. It's one reason why when we study medicines, we test them out on mice to see how they might work on human beings, because 99% of that construction of that organism is similar to us. And so in the same vein, we can study the sun, because 99% of the characteristics of how our sun works is similar to how other stars would work as well. To characterize other stars, though, we need to know that they are very far away, and there are 3 celestial coordinates that will identify their position in the universe from us, and that is right ascension, declination, so we can get the angular position on our celestial sphere, and, of course, distance. Distance would be that 3rd coordinate we don't think about too much when we look out in the sky, because it's something you just can't really discern from the naked eye. But distance, how far are these objects away from us? They're vastly different in distance. So we have these 3 coordinates that will place them somewhere in the 3-dimensional universe: right ascension, declination, and distance. Celestial distance is that more intriguing coordinate, as we said, because it's not an obvious thing to the human eye. We can measure in astronomical units, light years, or parsecs. Astronomical unit is the distance from the Earth to the Sun. That is the shortest distance that astronomers would use. It's the mean distance between the Earth and the Sun, 1.5 times 10 to the 8 kilometers. I don't know why they don't use the nice distance between the Earth and the Sun as opposed to the mean distance between the Earth and the Sun. The light year is the distance light travels through a vacuum in 1 year. That's approximately 10 trillion kilometers, 9.5 times 10 to the 12 kilometers. That's a light year. Light traveling at 186,000 miles per second, traveling for a whole year, is a pretty far distance. A parsec is even further. Parsec is the distance to a star when the star exhibits a parallax of 1 second of arc, and it's 3 1/4 light years. So as we go into greater distances, we go from an astronomical unit to a light year to a parsec. That's alphabetically in order as well, A to L to P, and we're going to a greater distance as we go in that progression. Here's a look at the distance from the Sun to the Earth, 1 astronomical unit. If we greatly increase that, say the distance traveled by light in a year is 1 light year, and increase that to 3 1/4, then we have a parsec. A parsec is 3 1/4 light years and approximately 1/5 of a million astronomical units. So it's approximately 200,000 times the distance of the Earth to the Sun. So if you want to measure a star, a nearby star, if you will, by using parallax, you measure the angle of parallax. the angle of parallax, is designated by rho here, is the parallax angle in seconds of arc. And then if you did that, in other words, what you would do is you'd measure the star's position against a backdrop of further stars, and you measure that in January, and then 6 months later in July, if you measured that angle, which would be half of that total angle that you measured, which is your parallax angle, then we define the distance in parsecs as 1 over that angle of parallax angle that you measure. And that angle is measured in seconds of arc. For instance, calculating the distance in parsecs to Sirius, the bright star in the sky, annual parallax is 0.376 seconds of arc, less than 1 second of arc. The distance is 1 over 0.376, or 2.66 parsecs to Sirius. Here's another example. Calculate the distance in parsecs to Proxima Centauri, which is the nearest star to Earth. It is the small neighbor star to Alpha Centauri. Annual parallax is 0.762 seconds of arc. So 1 over 0.762 is 1.31 parsecs. So even the nearest star to us is still greater than 1 parsec away, 1.31 parsecs away. And since they're about 3 1/4 light years to a parsec, this is 1.31 times 3.25, or about 4.2 light years away. That means to get to the nearest star after our sun, you would have to travel at the speed of light for 4.2 years to get there. Our sun, in contrast, is only 8 light minutes away. Here's another way to look at this. Distance to Proxima Centauri is 1.3 parsecs. That's 270,000 astronomical units, or 270,000 times the Earth-Sun distance. So if you were to measure the Earth-Sun distance on a scale of, say, about 1 meter, which would be about this far, maybe the distance of this behind me, then our next nearest star after the sun would be located 270,000 meters away, which would be down in Montgomery, Alabama. So if the Earth-Sun distance were 1 meter apart, the next star would be down in Montgomery, Alabama. That's how far the next star is away. So that's why we should study our sun to study stars, because then even the closest star after that is too far away. In the sun's neighborhood, there are 30 stars within 4 parsecs of the sun. That's still quite a distance away, and only 30 of them within that distance. We can measure distances to over 100 parsecs if we use adaptive optics. Adaptive optics is a way to account for the Earth's atmospheric effects by either computer enhancement or the movement of secondary mirrors to account for all these effects of the Earth's atmosphere. We can do better if we go outside the Earth's atmosphere. The Hipparchus satellite, which is measuring distances to stars, can extend the range to over 200 parsecs, so to twice as much. And hopefully in the near future, we'll have space missions that can send out telescopes that can measure up to 25,000 parsecs away, or that would be close to about 100,000 light years. Two closest stars to us are Proxima Centauri or Alpha Centauri, that double star, and after that, Barnard star. But less than 100 stars lie within 5 parsecs of our sun. Barnard star is about 8 light years away. Alpha Centauri is around 4. If we were to determine astronomical distances, for closer distances, we could just use radar ranging. So say if we wanted to find the distance to Venus, say, we could use a radar, send a signal, bounce it off Venus, and have it come back and measure that distance by the time it took for that signal to get there and come back. That is radar ranging. For close enough distances, say within our solar system and our near solar system, we could use that. If we want to go a little bit further away, we could use trigonometric parallax or stellar parallax, and that's just measuring the parallactic angle and figuring out the distance as 1 over that angle measured in seconds of arc. So that trigonometric parallax is better for nearby stars if you can actually measure that parallax, but we're already talking the near stars less than 1 second of arc of a measurement, so that is a very difficult measurement to make. But we can also find the distance by spectroscopic parallax using the width of spectral lines to estimate the density, size, and luminosity of distant stars. For spectroscopic parallax, what we would do is create what we call a HR diagram, which will be in the next lecture on this chapter. But with that HR diagram, we could measure the luminosity of the star as a function of its temperature, and then calculate its distance based on that. So that would be spectroscopic parallax. Say you see a star out there, it's moving, and it's moving with respect to us. There's 2 ways it could be moving. It could have 2 components. One is it could actually be moving away from you, which would be radial velocity, or it could be moving along your line of sight, which would be a transverse velocity. Now, transverse velocity would be easier to see if you were to try to take a picture and see that. A radial velocity would be almost impossible to see visually because it's moving along the same line of sight as your line of sight. So you would have to use a different procedure to measure that velocity. You'd have to use a Doppler shift to measure that velocity. But transverse velocity, you could measure the distance the distance that it moved transversely. If you knew its distance radially, you could calculate that transverse velocity. So a transverse velocity is associated with what we call proper motion. It's the motion that a star makes in a transverse direction over the course of 1 year. Proper motion, here's the general definition: the angular movement of a star in seconds measured on the same day each year. So if you took a snapshot of the sky, took the snapshot a year later, and saw how far a star had moved with respect to the very distant stars behind it, then you could measure its proper motion. And this would be different from parallax because you would do it on the same day each year. So there's no parallactic angle to it. It's actual motion. It's very small because of the large distances. Proper motion can be combined with the star's distance to calculate its transverse velocity. Any parallax measurement would have to be correct for proper motion. So if you made a parallactic measurement over time, you would have to also know the proper motion of that star so you could be most accurate with a true parallactic measurement to figure out distance. Here's an example of proper motion. If we look at Barnard's star, which we said was the second closest star to us, here's how it looks over a 22-year interval. Has the largest proper motion of any star, hence it's the fastest moving star we observe. So here's how it was in 1 year, and it moved above this bright star here after 22 years. So it moved that distance, that red distance right there. That's pretty small. That's 10.3 seconds of arc per year, and that would be its proper motion. But it's extremely small to measure. That's something you'd have, if you were an astronomer, you'd have to be pretty accurate, and you could do that. Doppler shift, something we talked about earlier in this semester. Doppler shift can tell you whether something's moving away from you or toward you. Like this tornado here, we know that one side of this tornado is moving away from us. Normally tornadoes go counterclockwise, 99% of them do. So you can see this green effect of that part of the tornado moving away from you, and the red is that part of the tornado moving towards you, so we know this thing is rotating. So the Doppler shift can determine radial velocity. It can tell you how fast something is moving towards you or away from you. As it relates to the light from stars, what you would do, since most stars, or the majority of stars that we'd be looking at, 9% of the stars out there, would have hydrogen in them. So if we looked at the characteristic lines of hydrogen, we know what those lines look like when they're at rest in the laboratory compared to us. And so if we look at a particular star, we can see how much it is shifted, its pattern is shifted, in relation to a stationary pattern in relation to us. And so if we measure the amount that it shifts by, the change of wavelength that it shifts by, then the ratio of that change of wavelength to the true wavelength of the hydrogen multiplied by the speed of light will give us the velocity of the star radially as it's either moving away from us or towards us. So that is this is actually a simplified version, but it's a nice, accurate version of how fast a star would be moving in relation to us, and that would be a simple measurement for an astronomer to do. But that would be a Doppler shift measurement. One way to name stars is to look at their constellation and measure them, name them according to alpha and beta and gamma, and within a constellation. But if you truly want to be universal and accurate, now you would just say designate its declination and right ascension. So on the celestial sphere, as you're looking out, you just measure how far this way and how far that way to go, and there's the position of the star, declination and right ascension. But if you want to know exactly how bright something is, its true brightness, then that depends on distance. So how bright a star appears to us depends on its absolute brightness and how far away it is from us. And we know that the apparent brightness is inversely related to the distance squared from us. So how apparent something appears in brightness will depend on how far away it is from us. In other words, the light is diluted as it gets further away from us. If we went from a light source and we distribute that light over a square, and then we increase our distance to twice as much, now the light is distributed over 4 times as much area. Hence, its luminosity is only 1/4 as much. And if we went 3 times as far away, I was saying if we went out to 3 times as far away, then that light source would be diluted to 9 times as much area. Hence, its luminosity would only be 1/9 as much. So the luminosity is proportional to 1 over the distance squared. In other words, it's inversely proportional to the square of its distance from us. Here's that example. If a star were moved 2 times further away from us, it would only be 1/4 as bright. And conversely, if a star were moved to 2 times closer to us, it would be 4 times brighter. Well, the apparent magnitude scale, the way that the brightnesses of stars appear to us as you look out in the sky, this scale was invented by the Greek astronomer Hipparchus. And on this scale, naked eye stars were classified into 6 magnitudes. So Hipparchus looked at all the stars that he could see in the sky and put them into 6 categories, 6 magnitudes. The brightest stars were classified as 1st magnitude, the brightest stars in the sky, 1st magnitude. The dimmest stars were classified as 6th magnitude, and all the stars in between were in between. Now it's been shown that accurate measurements show that about a first magnitude star was about 100 times brighter than the sixth magnitude star. So as we continue to use this scale, a magnitude difference of 5 from 1 to 6 corresponds to a factor of 100 in brightness. So that means each magnitude difference of 1 corresponds to the square root, or the fifth root of 100, which is about 2.5. Fifth root of 100 is about 2.51, so we can just round that to 2.5 and say that every time that you move 1 on the magnitude scale, you're going a factor of 2.5. For example, now Sirius has an apparent magnitude of about -1. Polaris has an apparent magnitude of +2, so there is a 3 orders of magnitude difference between those two stars. Which star appears brighter and by what factor? Well, magnitude gets brighter as you go lower in number. So Sirius is a brighter star than Polaris, and it's brighter by 3 magnitudes, which means that it's brighter by a factor of 2.5 times 2.5 times 2.5, or a factor of 15.6. Sirius is 3 magnitudes brighter and a factor of 15.6 times brighter than Polaris. Sirius is one of the brightest stars in the sky. Well, obviously, since we're looking at Sirius, there are objects that are brighter than magnitude 1, Sirius being a magnitude -1. How can we get a -1 magnitude? Well, astronomers found that there were some objects that were brighter than this scale of 1 to 6, and hence if you continue the scale, making things that are brighter by a factor of 2.5, 0, say, and then brighter than that by a factor of 2.5 and -1, then you can go beyond this scale of 1 to 6. And some objects are so bright that their apparent magnitudes are indeed negative. In particular, the planets, when they're near opposition, can get to be pretty bright on the negative scale of things. Venus at its brightest is a -4.4, which is pretty bright. The moon is a brightness, a full moon would be a brightness of about -12.5, so that is approximately 8 magnitudes brighter than Venus, which would be 2.5 times 2.5 times 2.5, 8 times. So that's, what is that? Let's try that out. 2.5 to the 8th power is a factor of 1,526. So more than 1,000 times brighter than Venus. And the Sun carries that even further. The Sun has an apparent magnitude of -26.8. So we're talking, a factor of 100 for every 5, and the Sun is more than 10 magnitudes brighter than the Moon, so more than 100 times 100, or more than 10,000 times brighter than the Moon. Here's a look at it. Here's the apparent magnitude scale, our Sun being the brightest object on this apparent magnitude scale, the full Moon being the second brightest object, and Venus at its brightest would be the third brightest object. Sirius being the brightest star in the sky, we have at a -1.5 here. Alpha Centauri is pretty bright too. You can't see it in your sky because Alpha Centauri is in the southern hemisphere, but it is one of the brightest stars in the sky. Absolute magnitude is equivalent to the actual luminosity of a star. It's defined as the apparent magnitude we would see for that star if we were put at a particular distance of 10 parsecs away from us. So we'll put everything on the same scale, make it absolute, put all objects 10 parsecs away from us, and see how bright they are. This can be calculated if we know the star's apparent magnitude as we see it, and its actual true distance from us. And then we can recalculate to see how bright it would be if it were put at this absolute distance of 10 parsecs away. So this allows for a direct comparison of the luminosity of all stars on the same scale, an absolute scale. And this is what we want to use if we want to compare stars to each other. For example, due to the inverse square law, an increase in the distance by a factor of 10 would decrease the luminosity by that distance squared by a factor of 100, say. So if a star were 10 times further away than, say, another star, it would decrease its luminosity as we see it by a factor of 100. And increase its apparent magnitude by 5, but its absolute magnitude could be much lower. So on this scale, we have a mathematical relationship where the apparent magnitude is equal to the absolute magnitude plus 5 times the log base 10 of its distance in parsecs divided by 10 parsecs. You don't have to know that, but that's how we would calculate the apparent magnitude based on its absolute magnitude, or vice versa. Go from one to the other. We'll note that at 10 parsecs, the log base 10 of 1 is 0. So at 10 parsecs, the apparent magnitude is actually equal to the absolute magnitude of the object, which makes sense. Here's an example, Betelgeuse. For Betelgeuse, its absolute magnitude is minus 5.5, which means that if Betelgeuse were put at 10 parsecs away from us, it would be a pretty bright star. It would be brighter than Venus is at its brightest. It would be, in fact, a factor of 2.5 times greater than the brightness of Venus at its brightest, if it were placed 10 parsecs away. But Betelgeuse is much further away from us than that, so it never looked that bright. Its distance is actually 489 light years, or 150 parsecs away. So if we put that into this formula, distance being 150 parsecs away, then we'd have a negative 5.5 plus 5 times the log of 15, which is 10 to the 1.176 power times 5, gives us an apparent magnitude for Betelgeuse of 0.38. Still pretty bright. That's on the order of 0, which is brighter than that absolute magnitude scale when it was first set up, 1 to 6. So that makes Betelgeuse one of the brighter stars in the sky. In fact, it's the ninth brightest star in the sky. And it's really one of the most visible stars in the sky because it's on the edge of the constellation Orion, the 9th brightest star in the sky. So on an absolute magnitude scale, our Sun would have an absolute magnitude of around 5. So normally our Sun would be pretty bright on a apparent magnitude scale, but on an absolute magnitude scale, it would be pretty dim, and it would be just barely visible to the naked eye if it were put 10 parsecs away from us. Betelgeuse, on the other hand, which is already pretty far away, but it's so huge that it's still pretty bright in our sky, would be, normally it's pretty bright as a star, but it'd be really bright if it were put 10 parsecs away because it'd be so huge at that distance. So it'd be much brighter than our Sun would be at that distance. And Barnard's star, which has a absolute magnitude of 13, would actually, since it's closer than 10 parsecs away, would be much dimmer if we were to place it at 10 parsecs away from us. Here's a look at a picture of Betelgeuse. We can actually measure by speckle interferometry its actual size. And we can see that the size of Betelgeuse is on the order of Earth's orbit around the Sun. So we think of the Sun and the Earth being 100 sun diameters away from the Sun, but the Earth's orbit, if Betelgeuse would be a star that would fill up the whole space between the Sun and the Earth. It would be that large. So it's a huge star. We have giants. Giants are stars with radii between 10 to 100 times that of our Sun. So Betelgeuse would be a giant star. We have supergiants, which would exceed 100 times the radius of our Sun, and maybe up to 1,000 times that of our Sun. That would be a supergiant star. Dwarfs will be stars whose radii are comparable to our Sun or smaller. Here's some examples. Here are some giant stars. Mira, 80 times our Sun's radius. Arcturus, 23 times. Capella, 10 times. These are all larger than our Sun, between 10 and 100 times the diameter of our Sun. We have dwarfs, which includes our Sun, and smaller stars. Sirius B, which is the dwarf companion to Sirius. Barnard star, which is only about 7/100ths the radii of our Sun. We got Jupiter in here, but that's not really a star. Proxima Centauri, which is the white dwarf companion star to Alpha Centauri. And then we have the supergiant over here, Antares, which is that major bright star in Scorpio. The scorpion, say Antares, the ant goes with Scorpio. And we see that if it were put on the scale, it would actually fill to the orbit of Mars. So Antares is so large, it would fit within Mars' orbit, much larger than it would engulf us if our Sun were Antares. The color of a star is determined by its surface temperature, and the surface temperature of the star is determined by measuring its apparent magnitude. At different wavelengths, and by fitting the correct blackbody curve to the points, colors of stars from hottest to coolest go from blue to white to yellow-orange to red, blue being the hottest, red being the coolest. Hence, we want to measure blackbody curves. Stars are black bodies, so their temperature relationship, their intensity relationship to the frequency of light that they put out is the skewed curve that looks like a blackbody curve, the maximum of which is given by Wien's law. The frequency of that maximum is proportional to the temperature of the star. As we go to higher frequencies, the star gets hotter. So go to lower frequencies, the star gets cooler. So the maximum of this curve determines the temperature of the star, which is something we would want to know. If we were to measure the light of a star using two filters, a blue filter and a yellow filter, we could determine 2 points, intensity related to the frequency of those filters, and those 2 points are all we need to determine the whole blackbody curve. It's like 2 points determine a line. Well, these 2 points would determine the whole curve because it's a mathematical relationship for that curve. So all you need is 2 points. And so hence an astronomer would use 2 filters, measure these 2 points, find their intensities, and then measure the whole blackbody curve for that star, and hence measure its maximum and hence its temperature of that object. So that would be the easiest way to measure the temperature of a star that's far away. Hence, you can relate the temperature to the blackbody curve. Say if you're looking out here and you were to measure, say, a red dwarf, which is something you wouldn't be able to see visually, you measure that blackbody curve and you see it does not intersect the visual spectrum. So that would be something that you wouldn't be able to see with the naked eye out in the sky, but you could measure using instruments in the infrared, and you would measure and find out that the temperature, in this case of its surface, was 60 Kelvin. That might actually not be a red dwarf, or maybe a black dwarf actually. Here's a red dwarf. Oops, let's go back. Here's a red dwarf where you just barely could see it using, say, instruments in the infrared, but its true maximum is in the infrared, below the visible spectrum, temperature about 600 Kelvin. Here's a blackbody curve for our sun, which peaks out in the visible range, which is, biologists would tell us that that's why we're so sensitive to the visible range. And that gives us a temperature at that point on the surface of 6,000 Kelvin. And here's a cluster out there, which would also be hard to see, since most of the light it's giving out is in the ultraviolet, which is beyond the visible range, but it does give out some light. Some of its intensity of the blackbody curve is in the visible range. It would appear very bright blue to us because it's so hot, but actually its peak is in the ultraviolet range at 60,000 Kelvin. If we adopt convenient solar units in which luminosity is measured in solar luminosities, luminosities of our sun, which corresponds to 3.9 times 1026 watts, radius is measured in solar radii, 696,000 kilometers, and temperature is measured in solar temperatures, 5,800 Kelvin, then it is true that luminosity is related to the radius squared times the temperature to the fourth power. For our sun, this would be a simple relationship. Radius of our sun is 1 solar radii, so that would be R1 squared, and the temperature of our sun is 1 solar temperature, which would be 1 to the fourth. 1 squared times 1 to the fourth is 1 to the sixth, which is 1 times 1 times 1 times 1 times 1 times 1 times 1, which is 1. So the luminosity of our sun is 1 solar luminosity. But we could use this for other stars, and that could be quite useful. Hence, we could find the radius of stars just by measuring their luminosities and their temperature. Temperature we can get from the blackbody curve. Luminosity we can get by its absolute magnitude. And so we can get the radius is equal to the square root of the luminosity divided by the temperature to the second power in terms of solar values. For instance, the red giant star, Mira, has a luminosity of 400 solar units, a temperature of 0.5, in other words, is half as cool as our sun. Putting this in this, we have the square root of 400 over 0.5 squared, 20 over 0.25, or 80, which means that the radius of Mira is 80 times the radius of our sun. So it's 80 times the diameter of our sun as well. That concludes the first lecture in this chapter 10 on stars. We've been focusing sort of on our sun in order to understand other stars. The next chapter, or the next part of this chapter, will deal with the HR diagrams and how we can relate luminosity to a star's temperature.